In the last lecture, we saw the formulation for a forced vortex, how the shape of the forced vortex is obtained, what is the pressure distribution in a forced vortex. And if you recall, the forced vortex is actually created when you apply an external force, right? And that can be formed only within a solid boundary. And today we are going to do free vertex, which does not require any solid boundary to be formed. However, this also forms when there is some sort of an external force. For example, there is a Coriolis force, right? So this happens when there is a non-conservative body force that is applied, okay, as we discussed in the last lecture. So what exactly happens in this case is there is a concentrated circulation, right? In case of force vertex, we apply a rate of rotation, right, and angular motion ourselves, and that converts into vorticity, and that vorticity makes a circulation, right? Whereas in this case, there is no vorticity, rather there is a circulation. So there is circulation which is actually a concentrated circulation which exists at r equal to 0. Okay, so basically you can assume that there is a circulation here, and that circulation is actually driving the complete flow field. Likewise, in this case, you can assume there is a circulation here that is at r equal to 0 or r tends to 0, and then that is driving the complete flow field. Okay, so that's why this is called concentrated circulation that occurs at r equal to 0 or r tends to 0. That is more precise. Okay, and that is why here also we can just write when r tends to 0, that is the radius. Okay, so if there is concentrated circulation, we can, based on this, we can also find the angular velocity of the flow. So let's assume that there is a imaginary vorticity omega, right? So we have seen previously that free vertex is an irrotational flow, and that means it has zero vorticity, right? And in the end of this lecture we will see why this is irrotational and why force vertex is rotational, whereas there is rotational moment, like there is angular moment, but even because after that this flow is considered irrotational, whereas force vertex is rotational, and in this case there is still some circulation which is there at r equal to 0 but not at other locations. So let's assume there is some vorticity omega that will give us angular velocity w as omega by 2, as you remember, and this gives us velocity, angular velocity as omega r. That actually means u theta is equal to omega r over 2. Okay, and we know that circulation must be equal to area times vorticity, right? This is something we have defined. That actually means that for any radius r, pi r square, and let's assume it has a circulation, a vorticity of omega, so this must be the circulation. Okay, that actually means that if it is pi r square and your omega can be defined as just one second, so we can pull this little this side, and let's first define omega with respect to, so this thing together gives us omega as 2 u theta over r, right? That is what we get, and that is why in this equation also we can simply multiply omega to be equal to 2 u theta over r. Okay, so this actually means that our circulation is actually equal to 2 pi r u theta, okay, which implies that u theta is equal to circulation over 2 pi r, right? So this is a relation we get between the angular velocity of the vertex, free vertex, with the circulation, where u theta, as we discussed, is the angular velocity at any r, and this is the concentrated circulation at r equal to 0, right? So circulation is at r equal to 0, but that is still driving the complete vortex flow, okay, and that is creating this angular velocity u theta. So now if you want to plot u theta against r, right, it will look something like this. So if this is your u theta, this is r, you can see u theta is proportional to 1 over r, right? So it will look something like this. So when u theta, when r tends to 0, u theta tends to infinity. When r tends to infinity, u theta tends to 0, right? So at r equal to 0, you have extremely high velocity, angular velocity, extremely large angular velocity, and as you go away from the source of circulation, you have very little angular velocity. And that you can imagine from this image that you have here, right? At the center of the circulation, there will be extremely large velocity, and that is something you might have observed when you see especially these atmospheric circulation here. Just intuitively you can imagine that there is extremely large velocity at the center, but as you go away from it, there is not much effect, right? So this is what happens. Your velocity is very large at the center, and it decreases as you go down. It becomes almost 0 as you go far away from the center location. Okay, so now let's try to derive a solution for this vertex, the pressure field, and what is the shape of the vertex, etc. Okay, and we are going to use the same set of equations that we used before. So these equations, but to be able to use these equations, we must make some simplification as we did for forced vortex, right? So here again we will assume that this is a fully developed vortex, so we are not considering the transient effect. We will assume that nothing is changing in time, so d by dt term will be 0, so nothing is changing with respect to time. And once it is fully developed, your ur and uz will be 0, because now it is fully developed, so there will be no flow from one radius to another radius, and no flow from one z value to another z value. So this happens during transient time when the vortex is developing or it is getting completely stopped. But once it is fully developed, there is no radial velocity and no axial velocity. Okay, and now there is axisymmetric case. Let's assume symmetric flow. That means your d by d theta, derivative of d by d theta will be equal to 0, but your u theta itself is not 0, because there is angular velocity, right? And that is something we already saw. This is your angular velocity, which is constant, and your d by d theta is equal to 0. All right, and now z value, gravity, right, that is g. We'll assume that is 0 0 minus g, so there is g in the z direction and 0 in other directions. Okay, so based on this, now we will make some simplifications. So your ur uz are 0, so this becomes 0, this is 0, and du by d theta is 0, so we will use the blue color here. ur is 0, ur 0, this is 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 0, and this is du theta, that is 0. All right, and this one is 0. Okay, so we have neglected all these terms, and in this case now your ur is 0, ur is 0, uz is 0, ur is 0. Okay, in du theta by dt is 0. Likewise here duz by dt is 0, uz 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 is 0, and also uz is 0. Okay, so in this case and then we have this equal to this one equal to minus rho g, and in this case du theta, this has to be 0, and this also must be equal to 0. This is equal to 0, and also this must be equal to 0 because that is d by du theta. Alright, so now we have made simplification, we have cancelled all unnecessary term, and this gives us a simplified equation. So first equation is gone, the continuity equation is not needed. Then from the second equation we have, let's call these as A, B, C. So from A we have minus u theta square over r is equal to minus dp by dr, and from B we have 0 equals mu 1 over r d by dr, r du theta by dr minus u theta over r square, and plus d square u theta over dz square. And equation C gives us 0 equal to minus dp by dz minus rho g. Okay, so these are the equations we are left with, and now we can make further simplification. We can assume that your u theta is equal to gamma over 2 pi r, where gamma is a constant. Okay, so now if you put this in equation B, 0 equals mu 1 over r d by dr, r d by dr, u theta as sigma over 2 pi r minus sigma over 2 pi r cube plus d square by d z square sigma over 2 pi r. We actually get that all these terms are actually 0, right? So here you can see this is a derivative with z, whereas it is a function of r. So this will simply become equal to 0 because r and z are independent variables. They don't differentiate each other. So that becomes 0. Why? Because r is not dependent on z. So r is basically a constant for z. Now these two terms, if you expand this one, that will become simply equal to this one. So this equation actually gives us 0, 0 on both sides. So equation B becomes of no relevance to us. Okay, because if you expand this term inside the derivative, or you basically if you differentiate it, that will give you exactly the same term as sigma over 2 pi r cube, and that will get rid of this equation completely. Okay, and that is why now we are left with equation A and equation C. So let me copy these equations. So that is equation A, and this is equation C. Okay, so we have these two equations left which are useful where other equations are of no use. So here we can try to find dp by dr as u theta square by r, where u theta can be written as 1 over r sigma square over 4 pi square r square. That will be u theta if you replace u theta with this term, right? And now we can integrate it on both sides. So this will give you basically sigma square over, sorry, lambda square, sorry, gamma square over 4 pi square comes out, and we are left with r cube dr, and that will give us gamma square 4 pi square, and this will become minus 2 r square, right? This is what we will get if we integrate it, plus let's say some constant c1. All right. uh, so that is an easy one, and now we can try the second one. Here dp by dz is equal to minus rho g, so p can be obtained as minus rho gz plus c2. Okay, so we have got two equations for pressure for free vertex case, right? And we are currently doing, just to recall, so this is the problem we are currently working on, and after making several simplifications and cancelling unnecessary terms in the Navier-Stokes equations, we finally got these three equations A, B, C, where B cancels out within itself, and we are left with A and C, and these two equations give us two basically formulas for pressure. So, right, where in this case, this C1 can be considered as a function of Z, and here C2 can be considered as a function of R, right? So they are constant in R. The C1 is constant in R but not in Z, and C2 is constant in Z but not in R. And that is why the actual pressure as a function of R and Z can simply be found by added these two equations. Okay, both the equations for pressure. So this gives us minus gamma square over 8 pi square r square minus rho g z plus some constant. And now this constant can be considered simply a constant. This is not a function of r or z. Okay, and it seems here again, like in the force vertex case, we have forgotten the rho value, one of the rho value, which actually comes from these equations. So this rho value that we have, not that one, this rho value we have forgotten. So there should be a rho here. Uh, there should be a rho here, right? So rho here, and I'll simply write that as rho here. So this is one density that we are missing. So please correct your notes. And now we can try to find what is the constant C. Okay, so to be able to find constant C, let's consider that this is our uh, vortex, right, where this side is water, this is air, right, this is water, or any other fluid, not necessarily water, but vortex fluid. Yeah, let's call it vortex fluid, or we can simply call it vortex. Okay, and here we will define this point as the origin, where r goes this side and z goes up, that means downward is minus z. All right, that is the center of the vertex. Let's put it precisely at the center. Now if you take this r further outward, basically this matches the with the vertex, right, and that is the interface of the vertex and the air, right? Above is the air, this is the vertex, and that means at the interface P must be equal to P atmospheric, right? So that is the definition. That is how we define P atmospheric or atmospheric pressure. So at the interface, pressure is P atmospheric, and where is the interface? That is at r tends to infinity, right? Because as we saw in previous case, like in here, how the velocity slowly decreases and it goes to infinity, and that is why pressure becomes P infinity only at r equal to infinity. So as r tends to infinity uh, and z equal to 0, P becomes equal to P atmospheric. Okay, and we are assuming z equal to 0 because this is how we have defined the z here, this point, right? So here this is actually z equal to 0 location. All right, and that is why this condition, once we apply, we can find the c value. So now if you put z equal to 0 and r tends to infinity in this equation, that will give us, if r tends to infinity and z equal to 0, this gives us P atmospheric equal to c, right? That this equation turns into, or in other words, c is equal to P atmospheric, right? And that is why we can rewrite that equation P of r comma z as minus rho gamma square over 8 pi square r square minus rho gz plus P atmospheric. Okay, so this is the pressure distribution in a free vortex. In a free vortex. Okay, so this is what we have. And now if you want to find the shape of the free vortex, right, if you want to define the shape of the free vortex, we will have to assume if P is equal to P atmospheric, right, that will give us the interface between the air and vortex, right? That will be the interface between these two fluids. So that will give us rho gamma square over 8 pi square r square equal to rho gz, where I'll pull it this side. So rho gz is equal to this, where P atmospheric and P atmospheric on two sides get cancelled. Okay, and that is why what do we get here is z is minus, the rho cancels out, gamma square over 8g pi square r square. So this gives you the shape of the vortex, right? And this is a hyperbolic shape. This is what we have seen. So let's go back and pick these two images that we have considered, or all of these images, let's say. Okay, so what do you see here is this particular curve that you see, that is the interface between the uh, air and the vortex, provided that this is your rz equal to 0 0. So this interface that you see in the red color is defined by this curve. Okay, that is a hyperbolic curve. And in this also you can visualize that this is how a free vertex looks like, right? As you can see from these two images, one is the vertex in water, another one is the vertex in the atmosphere, and this is how vertex looks like. Okay, and likewise if you want to find the constant pressure line, so as you can see here, all these lines that are defined, these are constant pressure line, right? So that you can actually simply use this equation. So uh, p as a function of r and z, and if you define a constant pressure, that will give you the value of z. So let's say, okay, so if you put p as equal to p1, that is, let's say, a constant value, that will give you z as minus lambda square over 8g pi square r square plus p atmospheric minus p1 over rho g. Right, so now this will give you the profile of this curve. If you assume this is your p1, let's consider that's p1. Now if you want to find the profile for this one, then you just put p equal to p2, and that will give you the profile of that one. So what you see here is the profile of that, the curve defining the constant pressure line. Okay, so now you know how the shape of a free vertex is obtained and why exactly we get this kind of shape, right? This is something we have seen in nature, both in atmosphere and in ocean, and now you know exactly why we see this particular shape and why not any other shape, right? And this, just to recall, this is happening because of a concentrated lambda value, right? Sigma, we have sigma here, lambda here. So these are concentrated circulation, right? That is there at r equal to 0, and that is driving the whole force. All right, and now we will also see for this particular case whether Bernoulli equation is valid or not. So validity of Bernoulli equation. So let's go back and take this equation again. Okay, and if you remember, we had defined u theta as gamma over 2 pi r, right? And that is why we can write this equation as p as rho gamma over, so it will become 2 u theta, right? If we convert this one, gamma over pi, so 2 will be left, and wait, I think everything will be there except the 2 parts, so 2 will come out, right? So that will give us u theta square okay minus rho gz plus p atmospheric. Okay, now if we bring these two terms this side, so P and also divide it by rho g, so that will give us this plus u theta square by 2 g plus z is equal to P atmospheric over rho g, right? And now you immediately see that because P atmospheric is equal to constant, your P by rho g plus u theta square by 2g plus z is equal to constant, right? And this is the Bernoulli equation, if you remember, right? This is the Bernoulli equation when your pressure term, velocity term and the elevation term are constant when added together, right? This means that free vortex obeys Bernoulli equation at all points, right? And why is that? Because it is an irrotational flow. Okay, so in case of force vortex, we saw that Bernoulli equation was still valid, but only on a streamline, right? Not everywhere else. And if you remember, for a rotational flow, Bernoulli equation is valid only on a streamline, but for an irrotational flow, Bernoulli equation is valid or constant at all locations, right? And that is why what you see here is Bernoulli equation, which is constant. Bernoulli function is constant everywhere because the flow is irrotational. Okay, and now you might be wondering, while we are talking about vortex, when there is circular motion or angular motion, and I keep saying that free vortex is an irrotational flow, whereas forced vortex is a rotational flow. So we will quickly discuss why we assume that or why it is happening. So in case of forced vortex, let's assume that this is our this is the shape we get, whereas in free vortex this is the shape we get, right? So this is from the side view, but if you look from the top, probably both of them will look something like this, right? Here also you see the same sort of flow. So in both of them we have angular motion or angular velocity, but the major difference actually comes in the fluid element. So let's consider there is a fluid element somewhere here. So we will assume it has a few different colors. So this side is red, this side is orange, and the bottom is green. Okay, that is the fluid element there, and we will assume we have similar kind of fluid element here. Okay, and now we know that this fluid element that you see is actually having having an angular motion, right? So the difference comes in these two cases is, I think I need to make this uh, rectangle little bigger for the left hand side case, because otherwise you will get confused. So here let's assume this is what we have. This is the fluid element. Okay, so this is what we have, and let's assume this is the same fluid element or similar fluid element in both the flow. Here also let me make it little bigger to make it more obvious. All right, so what happens is, once, so this is at, let's say, theta equal to 0. Okay, theta equal to 0 degree, theta equal to 0 degree, and this is theta equal to 90 degree, this is theta equal to 180 degree, and this is theta equal to 70 degree. Okay, and theta equal to 90, theta equal to 180, and theta equal to 270 degree. Okay, so when these elements are moving, it actually, in this case, it rotates like this. Okay, whereas in the right hand side case, it will still remain the same. It is moving. All right, and let's try to do that for this one here. All right, so this is the fluid element that we are talking about, right? And what do you see? The difference between the force vortex and free vortex is that in the force vortex case, your fluid element that you see, it is, while it is rotating, it is also revolving within itself, right? So uh, there is rate of rotation along the center, right, along this center, along the center of the vertex, but there is also an angular motion within itself, within its own axis, right? And that is why you see this was here, now this has basically rotated, whereas in this case, in free vertex, it is just translating. So it went from, it is started here, and it has actually just moved its position to this place. Now it has gone and changed its position to this place, so there is no angular motion itself, right? So there is, in left hand side case, there is translation plus rotation, whereas in the right hand side case, there is only translation. Okay, so the fluid element is only going from one place to another. Both it is going obviously in a different coordinate points, both in x and y, or r and z, but it is not rotating. Okay, within its own axis. So it is not rotating within this particular point, it is not, right? So there is no angular motion within itself, so there is not, but in this case there is angular motion within its own axis, that is this point. And that is why in case of force vortex, there is vorticity, okay, or the flow is rotational. Here vorticity is 0 and flow is irrotational, while complete flow is moving but not individual fluid element. And this one, in case of force vortex, it follows more like a thing called solid body motion or rigid body motion or rotation. This is also called rotation. So it moves just like a solid body, so it will rotate as they are all connected with each other, whereas in case of free vertex, that doesn't happen. Okay, so this is the difference between these two. So what we have done, this is for the force vertex case, and this is for the free vertex, right? And now you know what is happening, and why one is rotational, other one is irrotational, and that is why Bernoulli equation is valid in one case and not in the other. Okay, so this is the end of the vertex part, where we have seen how force vertex in a free vertex are formed. We have tried to derive equations to define the pressure field to find the shape of the vertex both in force vertex as well as free vertex. And we also tried to see how a Bernoulli equation is applied, and whether it is valid or not in one case or the other. Okay, in now if you know the shape or the pressure distribution, you can actually estimate what will be the velocity at different location, what will be the angular velocity, or what will be the depth of vertex is in case of free vertex, or in case of force vertex, etc. Like in case of force vertex, you can estimate how much water will go out from the glass if you start rotating, or in case of free vertex in the atmosphere, you can actually predict what is the depth of the vertex, or what will be the velocity, what area of the atmosphere around a vertex is getting impacted. Especially, during summertime you see more of this sort of vertex, and you can actually try to predict how much damage this vertex is going to bring to a building or nearby areas. Okay, so that's why these vertex flows are really important in predicting several environmental impacts of this kind of flows. Okay, next we will do porous media flows, which is a new topic.